Hey all, meet me again. Okay. As I told you in the class before, I will post a video about how to solve a previous exam problem. The problem that we are talking about is this one. Okay. I'm sorry that this exam problem is in Bahasa. Okay. But I believe all of you can still understand it. So basically, the things that we have to solve is this particular case, okay, where at A there is a pin there, B there is another pin, E there is another pin, D another pin, and at C, okay, here is a roller. Okay, so at C there, it's a roller. So that's the case that we have to solve. And one more thing, the one that is in question here for this particular problem is the moment diagram of this particular member, CDE. Okay, although the one that is in question is only moment diagram, but here in this particular tutorial, what I will give you guys is not just how to find out the internal moment diagram, but it's how to find out the internal normal force and internal shear force as well. Okay. And the problem here, the main problem here, actually there are two. Okay, the first main problem is to find out the reaction force at C, at D, and at E. Okay, those three. So because E is a pin, so it's supposed to be EX and EY. Because at D there is a pin, it's supposed to be DX and DY as well. And at C, because at C there is a roller there, it's supposed to be CX only. Yeah, but remember, with one free body diagram, we can only solve for 3 unknowns. In this case, we have 5, so we have 5, so we will not be able to solve it directly. Okay, that's the first problem. The second problem is normally up until now, what we learn is if the cutting is vertical, the beam that we are talking about, okay, the section that we are talking about is always horizontal up until now. So there's another problem, because this one, the cutting there will be horizontal. The beam there, the section there, this particular section from here to here will be vertical. Okay, so it will be slightly different than the previous one. That's why this problem is quite special. That's why I need to talk a bit about this particular problem. Okay, as usual, we have to start with drawing the free body diagram. The first free body diagram that we have to draw is this one. Okay, CDE. Okay, that's the first one. Then we have to add several other free body diagram in order to solve for the external forces. Okay, so let's discuss about it step by step. You can see here. Okay, this is the main free body diagram that we are talking about. Okay, as I told you, there are 5 unknowns: Cx, dy, dx, ex, ey. Okay, that's why we will not go to this particular, we will not use this particular free body diagram directly, because we will not be able to solve it. 5 unknowns with only 3 equations: sigma fx, sigma fy, and sigma moment. So we will not be able to solve it directly. That's why I will go to the other free body diagram first. Okay. So if we see the whole case, okay, you can see that actually we can try to solve for this particular free body diagram the member BE. Okay, the member BE there. At P there is a pin, so there will be PX and PY there. And at E there is a pin as well, so it's supposed to be EX and EY there. Okay, here I assume, right? I assume EX EY, okay, EX EY, EX EY comes from here, okay, comes from the first free body diagram. EX EY comes from the first free body diagram. That's why here, okay, first I define EX EY here going down and going to the left. Okay, that's why, because it's action and reaction, EY here is supposed to be going up, the opposite, and EX here is supposed to be going to the right, the opposite as well from this one. Okay, and if you ask me whether we should include this 300 Newton to this particular free body diagram or not, okay, if you draw it like me, like this, you don't have to. Why you don't have to? Because the 300 Newton, okay, which is supposed to be handled by the first free body diagram, actually is already included here at EX and EY. So you don't have to add the 300 Newton there. So here I assume that the reaction which is happening at the point E at the first free body diagram, member CDE, okay, it comes only from the pin EX and EY. Okay, 300 Newtons. I assume all the forces happening at the second free body diagram, member BE. Okay, so because of that, we can try to solve for EX and we can try to solve for this particular free body diagram. Although there are 4 unknowns, PX, PY, EX, EY, but at least we can try. Okay. You can see here, whenever we do something like this, because the number of unknowns and the number of equation is not matched, right? The number of equation is more than the number of unknowns. The number of equation is less than the number of unknowns. We will not be able to solve all the unknowns. In this case, we have to use good strategy. Okay, the things that I want to find, because my main concern is the first free body diagram. Okay, because my main concern is the first free body diagram. What I want to find is all the forces here, only those 5. In that case, I will try to find which one from this that is there in the first free body diagram. Okay, if you see it there, okay, if you see it there, only EX and EY, which is there in the first free body diagram. So that's supposed to be my main concern. I will try my best to find the value of EX and EY from this. Okay, now in that case, that's why I want to find the value of this. That's why I try to use sigma moment at P at this point. By using sigma moment at P, this is what I will get: 300 Newton multiplied by 0.2, okay, plus 300 Newton multiplied by 0.4, this distance, okay, minus EY multiplied by 0.4. Okay, as you can see in this particular equation. Okay, the results there, what I get is EY, the value of EY there will be 900 divided by 2, which is 450 Newton. So now I found one of the value that I'm looking for, EY. Okay, EY there is 450 Newton. Then I'll try to use the other equations to solve for the other unknowns. Okay, using sigma Fy equal to 0, okay, because EY is already known. Using sigma Fy equal to 0, and if going up is positive, what I will have is Py plus EY minus 300 minus another 300 will be equal to 0. Okay, this particular equation. Then after that, I can find out that Py, the value of Py will be 600 minus Ey, where Ey in the previous equation, sigma moment at P, I got already the value. I got the value of Ey already, 450 Newton. Here. So that's why my Py will be 600 minus 450, which is 160 Newton. So I already find Py and Ey. Now I want to find Ex, but unfortunately, there, if I use sigma Fx equal to 0, okay, Px is not known yet, so Ex will not be known as well. So we can't find the value of Ex as well. So using sigma Fx equal to 0, this is what I will get, Px minus Ex equal to 0. And in this case, what I will get is Px is equal to Ex. Okay, so later, in the next free body diagram, if I have Px in my calculation, I can replace the value with Ex. Okay, now we already used all the equation in the second free body diagram. Now we go to the third free body diagram. The third free body diagram will be this one. Member ABD. Member ABD. Okay, there we have several unknowns as well. At A, there will be AX and AY. At B, previously is already, I tried to solve it already, Py and Px. And at D, there is a dx and dy, which is already here. So Px and By is already here. So that's why the direction there, okay, the direction there, sorry, the direction in the direction here, I can't just put anything that I want. No, I can't. What I have to do, I have to put the direction of Px and By here, the opposites of Px and By in the second free body diagram, because it's action and reaction, right? So if here Py is going up, Px is going to the left, right? Now, in this case, Px will be going to the right, the opposite of this one. And By will be going down, the opposite of this one. Okay? The same thing for dx and dy. Dx is supposed to be going to the right, the opposite of this one, going to the left. And dy here is supposed to be going up instead of going down here, the opposite of that. Okay, it's supposed to be the opposite because it's action and reaction. Okay, for x and ay, you can put any direction that you want for that one. Okay, I don't care. Right now, for this one, remember that we already have the value of this one, Py, and Px here is supposed to be the same as Ex. Okay. Then, because what I want, right? What I want is this particular value, dx and dy. Okay. Because this is what I need in the first free body diagram, which we want to try, which we want to solve. Okay. That's why I use sigma moment at point A. Because Ax and Ay, I don't need those two values. I don't need those two values. So I use sigma moment at point A in order to eliminate those two values. Okay, sigma moment at point A, Ax and Ay. Then, after doing sigma moment at point A equal to 0, what I will have will be, if counterclockwise is positive, okay, counterclockwise is positive, Px multiplied by 0.2, okay, it's counterclockwise, right? Minus Py multiplied by 0.2 as well, clockwise, that one, okay, that's why it's minus. Then Then after that, due to this dx, we will get counterclockwise moment, dx multiplied by 0.4, because the moment arm here is 0.4. Sorry, the moment arm here is 0.4. Then dy multiplied by 0.2. The moment arm is 0.2, so this one. Okay. So the equation that I got will be like this, like what I wrote here. Okay. Px multiplied by 0.2 minus Py multiplied by 0.2 plus dx multiplied by 0.4 plus dy multiplied by 0.2 equal to 0. Okay. By doing so, and by by knowing that Py we already know the value. Okay, remember that Py we already know the value here, 150 Newton. And Bx, we know that the value is equal to Ex. Okay, we can replace Bx with Ex like this. Then replace By with 150 Newton. This value. Okay, this value with this one. And then divide everything by 0.2. Okay, I divide everything by 0.2. This is what I will get. Ex minus 150 plus 2 dx plus dy equal to 0. Then, after that, we can try to solve it. Not solving it because there are 3 unknowns there. So I can write it down like this. Ex is the same as 150 minus 2 dx minus dy. Okay. Now, let's return back to the first free body diagram. I do not need to use sigma fy and sigma fx here, because sigma fy equal to 0 and sigma fx equal to 0 here, because both will give me the so in both equation I will have ax and ay, which I don't want, which I don't need. Okay, that's why I don't need those two equations. So I will not use these two equations because I don't want to use ax and ay there. Okay, now let's try again to the first free body diagram. Okay, to this particular free body diagram. Ey, we already got value, remember, 450 Newton, right? Ex, right? Ex from the first free body diagram, combination between second and first free body diagram, combination of the second and first free body diagram, combination of the second and third free body diagram. Okay. I know that Ex is this. 150 minus 2 dx minus dy. It will be the additional equation that we need. Okay. So first, Ey is not unknown anymore. It's known value for 150 Newton. Okay. So if Ey is known value, now my unknown will be only Ex, dy, dx, and Cx. 4 unknowns. Okay. We have 4 unknowns. And how many equations that we have? 3, right? Sigma fx, sigma fy, and sigma moment. But remember, from the combination between the second and third free body diagram, we get additional equation. Ax is equal to 150 minus 2 dx minus 2 dy, where all of those unknowns are here in the first free body diagram. So in total, we have 4 unknowns, and we have 4 equations as well. So we can solve it. Now let's try to solve it, right? Using sigma moment at d. Okay, I use sigma moment at d because I already know the value of Ey. By doing so, I can eliminate everything beside Ex and Ey. Okay, that's why I will be able to find the value of Ex using sigma moment at d. Okay, by doing so, if counterclockwise positive, Ex multiplied by 0.2 minus Ey multiplied by 0.4 equal to 0. That's sigma moment at d. Okay, and by doing so, I will get that the value of Ex will be 2 Ey. where EY is 450 newtons. So the value of EX will be 900 newtons, this value. This is the value of EX. Okay, now our unknowns just left, we just left with these three unknowns, dx, dy, and cx. Okay, then because I already found out the EX is equal to 900 Newton, I can try to find out dx, I can try to calculate dx by using sigma fx equal to 0. Sorry, not that sigma fx equal to 0. I'm so sorry, because we can't do that because cx is there as well. So by using sigma fy equal to 0, because the y component here is only ey and dy, where ey's we already know the value. So we can find the value of dy using sigma fy equal to 0. If going down is positive, dy plus ey equal to 0. Okay. Because of that, we know that dy is minus ey, minus 450 newtons. The meaning of minus there means that the direction is opposite of what I draw here. It's the opposite of what I draw here, with the value is the same as ey, 450 newton, but going up. Okay. Then after that, after solving dy, we can try to solve for dx and cx. Okay, but remember, okay, remember, we will not be able to solve it directly because, okay, we will not be able to solve it directly, sigma fx, because if you just use sigma fx equal to 0, what we will have is ex plus dx minus cx equal to 0. Where in this case, ex is already known, but dx and cx is not known yet. So we will not be able to solve that. Okay, so what I will do is to use the previous equation that I have, ex equal to 150 minus 2 dx minus dy. Okay, why I use that? Because I already know the value of dy, and I already know the value of ex. Okay, by doing so, by using this equation, I will be able to find the value of dx. Okay, using this equation, the same equation as this one, the same as the equation that we got before actually. Okay, ex is equal to 150 minus 2 dx minus dy. Okay, ex is 900 Newton. Dy is minus 450 Newton. That's why my equation became like this. Just input the value there. Then I can calculate for dx. So the value of dx is minus 150 Newton. What's the meaning of minus? The same as before. Means that the direction here is supposed to be the opposite. So it's supposed to be 150 Newton going to the right. Okay, 150 Newton going to the right. Then, because I already find out the value of dx, now I can solve for cx using sigma fx equal to 0. Okay, if going to the right is positive, so cx minus dx minus ex will be equal to 0. Okay, this equation. Then by inputting all the values for dx and ex, I will be able to get this one. Cx is equal to dx plus ex, and because dx is minus 150, I put it here. And because ex is 900, I put it here as well. So in total, cx will be 750 Newton. So the direction is correct. To the right, 750 Newton. That all of this, okay, all of this, by knowing all of the value here, then what I will do next is to draw the last free body diagram, which consists of the final value of all of those with the correct direction. Okay, you can see this is the free body diagram with the correct direction. So 750 Newton here going to the right, 150 going to the right, 450 going up, 900 going to the left, 450 going down. Okay, that's all the input that we need. Okay, now if we already have the free body diagram, we can try to solve it now. We can try to solve for the moment diagram, internal moment diagram, internal force diagram. Although in the questions, the one that is in question is only the moment diagram, but here I will explain to you guys how to find out the internal force diagram as well, even though it's not asked in the question, but I will explain to you guys anyway. Okay. As this is the problem. So there will be 3 cuts, right? The first cut will be here, the second cut will be here, and the third cut will be here. As I told you before, the special one will be the third cut because the cut is not vertical but horizontal because the section there is vertical. Okay, and then for the first cut, we always try to start with the first cut. Okay, this will be my free body diagram. Only 750 newtons going to the right, and then the distance there will be x. The distance from the left edge to the cut will be x. Okay, this is like what I defined here. The distance from the left edge will be x, and then before going to the first cut as well, sorry, I forgot about something. In the main free body diagram, I define as well, in order to simplify the calculation, I define as well that from this part going up, the distance there, okay, this particular point, from this particular point going up, okay, the distance there will be x-axis, okay. So if we use x, right, if we use x, the x there, okay, at here is x equal to 0, here is x equal to 0.2 meters, here is x equal to 0.4 meters, here is x equal to 0.6 meters, here is x equal to 0.8 meters. So the x, the distance x will keep going like this. Okay, it's keep going up, going up, going up. The value will keep going up like this. Then it will continue like this, going up as well. Okay, that's why if you see here, I draw the diagram. The distance there is 0.8 meters, so only 0.6 meters, because this particular part is in question as well. Okay, and in order to simplify the things, instead of using x for this particular part, right, I use x-axis, and I define that x-axis is x equal to x-axis is equal to x minus 0.6 meters. So at this particular point, x-axis is 0. At this particular point, x-axis is 0.2 meters. So at the same time, the x here is 0.6 meters. The x here is 0.8 meters. Okay. Now, let's try with the first cut. This is the free body diagram. Okay. The external force is only 750 Newton there. Then, as usual, because I put all the forces and moment at the right side of the cut, positive V is going down, positive normal, positive axial force is going outwards, and moment is going counterclockwise like this. Then using sigma fx equal to 0, and going to the right is positive, what I will get is n plus 750 is equal to 0. In this case, my axial force will be minus 750 Newton. Okay. That's why you can draw it here from x equal to 0. Remember, this is for x equal to 0 until okay, from x equal to 0 until x equal to 0.2. This one you can see from x equal to 0 until x equal to 0.2. The value of n there will be, sorry, I made a mistake, sorry. the value of n there from x equal to 0 until x equal to 0.2, the value of n there will be minus 750 Newton. Okay, then using sigma Fy equal to 0, because the only vertical force there is only V, we will get that V is equal to 0. That's why I draw it this way. From x equal to 0 until x equal to 0.2 meters, the value of V will be 0. Shear force will be 0. Then the same thing for the moment. Sigma moment at the right side here, sigma moment at the right edge here equal to 0. So moment m there will be the only moment. So m is equal to 0 as well. This is it, this part. From x equal to 0 until x equal to 0.2 meters. Okay. Then let's continue with the second free body diagram. The second free body diagram, I use the left side of the cut, this part, the left part of the, the left side of the cut, that one. And this is the free body diagram. Okay, the external forces there will be 750 from this one, 450 from that one, and 150 from this one. Okay, those are the external forces. Now we can try to solve for V, N, and M. Okay, using sigma Fx equal to 0. There, what I will have if going to the right is positive. What I have is N plus 150 plus 750 will be equal to 0, this one. So my axial force value will be minus 900 Newton. Okay, that's why here, this is what I draw here. Because this one will walk from x equal to 0.2 meters until x equal to 0.6 meters. Okay, this is what I got here from 0.2 until 0.6. Okay, then using sigma Fy equal to 0, what I will have will be, if going down is positive, V minus 450 equal to 0. Okay, so my V value will be 450 Newton. So it will be constant. This one from x equal to 0.2 until 0.6, 450 Newton. The shear force is equal to 450 Newton. Then sigma moment at the right side here, at right edge here, equal to 0. If counterclockwise is positive, okay, counterclockwise is positive, what I will have will be moment, okay, minus 450 multiplied by the distance there. If from the left edge to the cut here is x, and from the left edge to the 450 Newton is 0.2 meters, the distance this part will be x, right? X minus 0.2. Okay, so that will be our moment arm. Then, so m minus 450 multiplied by the moment arm here, x minus 0.2 meters. This one. Okay, so what I will get will be m is equal to 450x minus 90. Okay, then I'll try. Then I find it at x equal to 0.2 because I know that the equation here is linear. So by just getting 2 points, it will be enough for me to draw the linear line. So what I draw will be the one end, the linear line at one end at x equal to 0.2 meters, and the other end at x equal to 0.6 meter. At 0.2, by substituting value of x equal to 0.2 here, what I will get is 0. Because 450 multiplied by 0.2 is 90, minus 90 is equal to 0. This one. This point is 0. Okay, then after that, at x equal to 0.6, I substitute the value of x equal to 0.6 here. 0.6 multiplied by 450, the value will be 270. 270 minus 90. 270 minus 90, the value will be 180 Newton meters. Okay, so at x equal to 0.6, the value there will be 180 Newton meters. This one, 180 Newton meters. That's why this is my linear moment line, moment diagram for this particular section. Then the last part, okay. Okay, as I told you, oh, sorry. I accidentally pressed it. Okay, as I told you, the last one is slightly different because the cutting is horizontal, because the section there is vertical, and this is the free body diagram. I use the top part of the cut, this one, instead of the bottom one, because I don't want to draw the other forces. If you want to use this side of the cut, yes, you can, but you have to draw all the forces here until here. I don't want to do that because I'm too lazy to do that. That's why I draw this part. That will be my free body diagram. Okay, so there, this is my free body diagram. You can see here, this is my free body diagram. At the top, we have 450 Newton going down and 900 Newtons going to the left. Okay, and the distance there, because from this point to the cut is x-axis. Okay, the distance here from the top to the cut will be 0.2 minus x-axis. Okay, 0.2 minus x-axis. It will be 0.2 minus x-axis, like this one. Okay, and then I draw all the positive signs for V, N, and M. Okay, because the direction of the positive direction is going like that, right? My V positive will be like this, going to the left. My moment positive will be like this. The normal force, as usual, is always going outwards. Okay, using sigma Fy equal to 0. This is the weird thing. Okay, when you use sigma Fy, normally we try to find by using sigma Fy, we will be able to find out the shear force. But here, using sigma Fy, what we will get will be the normal force. Okay, what I have there is if going down is positive, what I have there is 450 Newton plus N equal to 0. In this case, my N will be, my axial force will be minus 450 Newton. Okay, that's a weird thing. Okay, using sigma Fy, you get the axial force instead of the shear force. Then using sigma Fx equal to 0, okay, what I have there is this and this. Okay, if going to the left is positive, V plus 900 Newton will be equal to 0. So my V, my shear force will be minus 900 Newton. Then using sigma moment at the bottom, this one, at the bottom edge, at this point, equal to 0. What I will get if the moment, counterclockwise moment is positive, is M from this one, minus 900 Newton multiplied by the distance. Okay, 900 Newton multiplied by the distance. Okay. The distance is 0.2 minus x-axis equal to 0. Okay. By solving this equation, what I will get is this one. Moment is equal to 180 minus 900 x-axis. Okay, then because I know as well this one, this equation is a linear equation. I check as well at x-axis equals 0. X-axis equal, remember x-axis equal to 0 here is the same as x equal to 0.6, okay, meters. By substituting x-axis here equal to 0, what I will get is 180 Newton meter for the moment. Okay, then xn equal to 0.2, or the same as x equal to 0.8 meter, okay, by substituting the xn equal to 0.2 here, so yeah, 0.2 here, what I will get there will be 180 minus 900 multiplied by 0.2. 900 multiplied by 0.2 is 180. So this equation become 180 minus 180, which is 0. This is 0. Okay. So this one is actually xn equal to 0.2 meters or x equal to 0.8 meters. So this particular point, okay, xn equal to 0 is actually this particular point in the main free body diagram. And then xn equal to 0.2 meters or x equal to 0.8 meters is actually this particular point at the main free body diagram. Then we will move to the equation, the diagram. Okay, the n there is minus 450 newtons for x equal to 0.6 until it is 0.8, or the same as xn equal to 0 to xn equal to 0.2. This one, minus 550 is then my V value will be minus 900 from this, from this to this, minus 900. Remember, okay, our x-axis starts from this part. This is x-axis equal to 0. That line is showing you the x-axis equal to 0. And this particular line, okay, showing you x-axis equal to 0.2 or x equal to 0.8 meters. Then the last one is this one. I have to draw that at x-axis equal to 0, this particular point. The value of m is 180, so this particular point. Then at x-axis equal to 0.2 meters, the value of moment will be 0, this one. So this is the line. So actually that's all. We got the moment diagram, shear force diagram, and normal force diagram. Okay, and let's check with our normal way. Okay, at this particular point, there's supposed to be jump in our shear force and axial force. Let's try. In the axial force here, there is a jump of from minus 750 to minus 900. So the jump there is 150. So it's correct, right? This particular jump is 150. It's the same as this one. It's correct. Okay. The same at that particular point. Due to this particular force, 450, there's supposed to be a jump in the shear force. And you can see here at this particular point is 0 to 450. So there is a jump of 450 here, which is the same as this one. So it's correct as well. Okay. And the last thing that we're supposed to check is at both ends. So the first end here, at this particular point, there's supposed to be a jump there from 0 to 750. So you can see here, there's a jump, 750, which is due to this one. Then at this particular edge, there's supposed to be a jump in the axial force. Axial force supposed to be 450. Okay, it's correct to do this one. Then the shear force, there's supposed to be a jump 900. It's correct as well to do this one. Okay, but remember, Okay, remember when you try to think about it, okay, don't do that logic. Don't do that logic for, okay, don't do the logic for this particular intersection, because there the normal force, okay, of the horizontal section will become shear force in the vertical section, and at the and on the other hand, okay, the shear force on the horizontal section will be the normal force on the vertical section. So we will not be able to put that logic there, because there is a change between normal and shear, because the definition of normal force or axial force is supposed to be in the same direction as your section, either tension like this or compression like this. Okay, that's a normal force. Shear force, on the other hand, is supposed to be perpendicular to the section direction. So if the section direction is like this, the shear force is supposed to be either going down or going up, because the section direction changing is from the horizontal section to the vertical section. Okay, the previous if in the horizontal section we try to look at the normal force, here it become shear force, okay, in the vertical section. And if we try to look for the shear force in the horizontal section, in the vertical section it will become a normal force. Okay, for the moment it will be still the same. Okay, I think that's all for the explanation of this particular problem. Hope it helps, and all the best for your exam. Okay, bye.